Thank you, thank you. This has been a huge pleasure for us, and it's great to see so many different domains taking serious problems on and actually making what, after I've heard the last 2 days, some real progress on some of these difficult issues. So let's keep it doing. Let's keep it going. So we are doing a research project in educational research, and I thought I'd tell you a little bit in the beginning about what's sort of going on in educational research and causal modeling in this domain, and then sort of fade into a more specific project that we're trying to look at, which is really to discover what mechanisms by which Martinez fractions tutor is actually working to teach fractions to 4th and 5th graders. So there's been all this new technology coming out in education, and it's producing data. Right? And we're beginning to have these really nice data sets in all different kinds of ways. We have computer tutors that are all around the country and the world now. We have online courses. You've heard of MOOCs. There's all sorts of others. And there's virtual labs that people are getting to use to work with unstructured, fun environments, and that's producing data too. So just give you a very quick sense of the sorts of things that are out there. In Pittsburgh, we have this NSF center called the Pittsburgh Sciences of Learning Center, and it's been around for almost 10 years now. And it's focused most of its work on exploring how these cognitive tutors that are based on theories of cognitive science from our own department, John Anderson's work in the 80s and 90s. And an offshoot of that work has been to build these tutors in algebra and geometry that are in high schools all over the country. There's now been about 600,000 students who have actually used these tutors in 3,000 different schools. And they're actually doing incredible things. In a recent evaluation done on 180 such schools, people taking algebra from all different backgrounds, not just rich kids in the suburbs, were learning almost twice as much as people who weren't using the cognitive tutors. So there's this really nice whole system, right, of building these tutors, and then a whole system of what data to collect in order to actually figure out what's happening inside or under the hood. Along with this sort of cognitive tutor effort, the Science of Learning Center has set up this thing called Data Shop, which if you have a cognitive tutor or an online course and you cooperate with them minimally, the data gets recorded and then dumped into this data warehouse, which is now storing about 500 different data sets that are all publicly accessible and available. So if you just go onto their site and choose one that you like and then write to the people, and if you get permission, you can download it and run it. And there's not only those data sets, but there's a whole bunch of tools that are available to use to analyze those data sets. From online courses, we've had this thing here called the Open Learning Initiative, and it's produced 25 college courses, lots of automatic data loading, lots of research studies. Now there's MOOC things you've heard about. One of them is Coursera. They don't do much about data collection that's going to be systematic. But edX, which is this joint effort of Harvard and MIT and a few others, they are actually taking seriously the idea of collecting lots of data and doing analyses of the type we've been looking at. There's virtual labs. This is a causality lab we built here. We have people go through it. They have no particular right answer and no right pathway. We can record what steps they've taken, log it, and then analyze what they've done. There's a chemistry virtual lab that's used here. Dave Yaron built, and it's just been incredibly effective. Even in looking at high school students and college students and looking at the number of engaged actions people have taken with the lab, right, that's explaining almost half the variation in the learning. So lots of different interesting stuff happening. And the kinds of data that we're seeing and are available range from log data, right? So when a student uses an online course and they do log in, or they visit a page, or they ask for a score, or they watch a video, we can record that and timestamp it. So we have these logs of their actions. We also have assessment data. Oops, wrong button. So we can get pretest scores, we can get intermediate assessments, midterm and final exams, etc. And then we have this problem-solving data, which is either unstructured in the virtual labs like I just talked about, or actually quite structured, right, if you're doing a cognitive tutor and you're looking at putting data into the data shop. And I'll get into that in a little bit in a minute. So here's an example of an edX log file, right? You can see that we're recording timestamps or time duration, different activities, but we don't have anything like a variable or a set of variables that one would customarily analyze in the kind of analyses you've all seen today. So one of the big challenges that we face is moving from these logs to something that's a set of variables on a population of individuals that we can actually then analyze with causal search methods. So in the cognitive tutors, the log files are much more structured. They actually require you to have a particular problem, and inside the problem a particular step, and then each step is associated with a component in what's called the knowledge component model, right, which is breaking down the task into a set of knowledge components you have to master in order to have the skills to do a certain set of exercises, and the activities and the problems given to you correspond to which knowledge components you do not yet have. Right, so that's part of the science underneath it. And the questions that are really, I think, facing this field involve partly how do we get variables that mean something from these raw log files, right? We don't have a variable like how much time did you spend per module or per page, or how much time did you spend watching as opposed to doing, things like that. We have to build that out of the actual log data, and we don't know what variables to build, and there's very little theory. And in fact, one of the things I think that separates this domain from certainly a lot of the others we've heard about, like biology, is we have really very little theory about what's what to go on. And so a lot of the utility, I think, in these methods is, right, the knowledge is weak. We need to find out more. We want to know what interventions, right, that we're going to be able to do as curricular interventions or tutorial responses that will actually help learning. So the questions are entirely causal. And we have this opportunity that's a bit unique, which is that we can do these experiments, take, right, the data, generate causal hypotheses, and then actually go out and test them, right? Unlike many other domains, it's quite easy to suggest causal hypotheses and then act on them to see if they come true. And we've actually got a couple for you today. And then the other question I'll also get to a bunch is, we have this question of by what mechanisms do learning interventions work among the interventions that we think we know actually work, right? So it's easy to do an experiment, randomized treatment, right? See an effect, but we don't know by what mechanism it's working. Okay, so one of the motivation that Martina and I have had on this project is, right, she's doing these series of experiments on this fractions tutor, and when she sees an open question, right, we get data, and we've applied causal model search, come up with hypotheses. She's done another experiment and tested that, and we keep going, and she's done how many experiments now? We've done 4 or 5? Something like that? 5 or 6, and hopefully we'll keep going. So I wanted to give you a couple of examples where we've actually applied model search previous to Martina, and then we'll go into the specific case of how fractions get taught effectively to elementary school students. So a bunch of us got together in the late 90s and early 2000s and built a whole semester course on causal reasoning to teach causal graphs, right? It's available in the online or the Open Learning Initiative as a whole semester course, and it involves lots of different interactive exercises, lots of different quizzes you can take, lots of different simulations, and we record, or we did record, things like the pre-test, the midterm score, how much comfort the students had with the computer, what race they were, their final exam, and things like how long they were logged in, what percentage of the voluntary interactive exercises they completed, right, ranging from 0 to 100%, as you would expect. And then other things like, back then in the 1990s, when you were going to read a module, instead of just reading it on the screen, you could actually say, print out the module. When it would print it out, you'd pick it up, go read it at home. But that would prevent you from actually doing any of the interactive exercises that were in the module, right? We didn't print those out. So we recorded how many print requests you made, and 12 other things at least that turned out to be completely irrelevant. But we didn't know that going in. So we took a bunch of these variables and we put it through the FCI algorithm, and what we came up with was that the pretest was known to be prior to the other variables. and it was connected in this structure. And print requests turned out to be positively associated with your pretest. So the better you came in as a student, the more diligent you were about printing out modules. But that turned out to be detectably a negative cause of how many voluntary interactive exercises you would do, as you would expect. Right? It didn't occur to us beforehand, but after model search, we said, oh yeah, we should have realized that. And that is an oriented edge, right? Because we know this is not an ancestor of this, because this was after the pretest. And we have, right, an independence relation here that allows us to orient that as an away from collider. So we had evidence from the algorithm that this is an unconfounded cause, and that's what we acted upon, because it turns out that we also have evidence that the number or the proportion of the voluntary interactive exercises you engaged in were actually crucial in determining how you did on the quizzes in the final exam. So we said, well, here's an obvious strategy. We can get people to do more of the exercises if we get them to print out fewer of the modules. So we did that, and in the next year following the data analysis here, we got in front of the class and we said to the students, you might be tempted to print out the modules, but if you do, go back and do the stuff online. Make sure you do the voluntary exercises and do the interactive stuff, because that's what's going to get you an A. Okay, students said, I'll listen to you about that, not much else. And so we collected a new data set and analyzed it in a similar fashion the next year. And it turned out, yes, that we had actually, this is a dashed line to indicate it's not significantly there, but it's still estimable. And it turns out that we've not only eliminated the edge pretty much, but reversed its sign. So now it was only the worst students, if anything, who were doing more printouts. But they were doing almost none anyway. And we broke most of this, right, not all of it. And the persistence of the effect of voluntary exercises in the final was, right, quite robust. And the overall scores of the students improved, as you would expect. So that was a happy outcome. The second thing that I want to talk about is sort of now going to go into the fractions project. And it involves searching for mechanisms by which these interventions might work. And the basic setup, I think, is we have in all these experiments, at least, right, the classical sort of, I'm going to randomize assignment of treatment. Right? So I have this experimental condition, and I know it's exogenous. Nothing causes it. It doesn't cause anything. I mean, nothing causes it. And I had this pretest I measure, and I know the pretest and the experimental condition, right, are disconnected. And I have a post-test, and I presume that the pretest, right, has some influence on the post-test. And I presume that the pretest and the experimental condition are both going to influence something that the student would do differently, and some way the student might understand the material differently. But I've drawn this fuzzy kind of cloud to indicate that when we start these endeavors, we don't really know, right, what behaviors are being affected by the treatment, and we don't know what sort of cognitive things are happening in their brain that might be helped by the experimental condition as opposed to the control condition. So one of the things we have to do that really turns out to be among the hardest is to try to figure out what might be ways to measure these mediators or these mechanisms, and then find a way to verify if we've actually measured the right stuff. Right? So we actually get a handle on where we might have evidence of a mechanism and where we might not. So there are other things that might be, right, confounders of the behaviors that the students change and the post-test performance, but hopefully we can measure some of them, and some of them we can't. Yeah?
Can you just quickly explain, maybe I missed, how the pretest would influence the student behavior or understanding?
So if you came in, if you came in as a student who was highly motivated and really academically qualified, right, and I came in as a student who was a slacker, right, then we would expect that even the experimental, whatever, right, the experimental condition did, that you would probably be more diligent, right, at practicing than I would. So if this was something like how much time you spent on the exercises, we would expect the pretest to affect that.
I'm sorry,
pretest is a proxy for some property.
It's more some Yeah, so that's...
Yeah, I mean, the pretest is a proxy for what you know about this domain, but that's going to also be a proxy for all sorts of other things. So in general, right, this ought to have an effect on, right, whether you're going to understand the material better than you see, whether I'm going to understand the material better, and maybe behavioral attributes as well. But perhaps this is a better way to put it.
Yes, that's...
Right. Now, I mean, it turns out that, you know, sometimes we can measure things that are relevant, sometimes we can't. So this is the big worry, right? If we have unmeasured confounding, right, then the relationship between these two guys, right, is, well, I'll get to that in a second. So just for an example, right, so suppose we measure, right, how much the student is engaged, how much time they're spending actually engaged, not just how much time, but really engaged. And suppose we also measure whether they're using the correct representation of this domain, whatever it may be. And we think that that's the correct causal structure. Well, then we should see a conditional independence, right? That the experimental condition and the post-test ought to be independent if we condition, right, on the pre-test, the student properties, and engagement and the correct representation, right? So that conditional independence ought to hold if we've got the right causal structure. But if we, instead of conditioning on engagement, we just condition on time, and this is the way the time actually figures, then the correct representation in time, even when we add these two in, will not screen off the experimental condition in the post-test. They'll still have a dependence left over.
Time is time on task.
Yeah, which we can measure quite easily. So I put this example in to show that we can measure time pretty easily. It's very hard to measure engagement or engaged time. Right? Now there's people working on this, like there's people like Ryan Baker at Columbia who are doing videos of the students, right, having independent people score whether they're looking engaged or not, and then try to look at the log files and do machine learning on whether we can look just from the log file behavior and make a good prediction about whether or not they're engaged. And actually they're making a lot of progress and they're getting reasonably well along in that, yeah.
So this is very different from the usual mediation analysis where you don't have a direct line from the experiment condition to the post-test results?
Right, I'm saying if there is a direct cause from an experimental condition to post-test, then you will not see this conditional independence.
So it's not this usual triangle with 3 steps?
Well, it is, but I'm saying if this is the correct model, then you will see this, and that will verify for you that you have picked up any effect from experimental condition to post-test going through these guys. So that's verifiable. And if you don't see this independence, then several possibilities exist. 1, there's a direct effect you've not modeled. 2, right, there's confounding that you've not included. 3, you've measured the wrong stuff.
But why are the pretest and student properties necessary in that conditioning?
Because if you go from here to here, and then up to here and down to here, right, condition on this is a collider now, it activates this guy, and then you have to condition on this to block this path. Right, so you have to condition on all these confounders, and that's what makes it really tricky. Right. So you sort of have this asymmetry whereby if you get the independence, you can confirm the fact that you've got a mediational, right, set of variables, but if you don't get the independence, you can't. Right? It's underdetermined why you might have missed that. Okay, so that's the basic setting. And so Martina has built this beautiful fractions tutor that is in the schools in 4th and 5th and 6th graders, right? Just in 4th and 5th graders. And one of the things that she's been very interested in this tutor is what the effect of teaching multiple representations is. Right, so usually you see number lines, you see pie charts, you see rectangles. Sometimes you only see one, and sometimes you see multiple representations. And Martina has been investigating whether teaching multiple representations and showing how they connect, right, is actually going to benefit learning. Because you'll have a deeper understanding of the domain of fractions if you can see different representations and make sure you can translate one into the other in various ways. So her first experiment was a 2x2 design with single representation versus multiple, and also prompting the student to explain why they did a certain thing, which has been shown in the literature to be effective in causing learning. And what was found was that in the self-explanation prompt and multiple graphical representation condition, we had the most learning. In the second experiment, she just did only self-explanation prompts and then found that, again, multiple representations were better than either of any of the three individually, right, where she taught each one to a different group. Okay, so we had pretty good evidence that multiple representations had a total effect on learning. And now, I have 0 minutes?
You said you wanted to know 20.
Okay. I'm almost done. No, I'm almost done. Okay. I can have a couple minutes, right? Yeah, I had a couple questions in between. So we know that. What mechanisms by which they might work? Well, in the standard ITS intelligent tutoring system literature, the mechanisms that are hypothesized and the variables to record those possible mechanisms are what error rate the students are making in practice, how many hints they're using from the tutors, and what time they're spending on these actual modules. So we actually went and go ahead and measured those things in these experiments, and we looked at trying to build a model in which, right, multiple representations as the experimental condition and standard, and in this case, self-explanation and their interaction, would be screened off from the delayed post-test and the post-test by hints, errors, and time. And it turned out that it was a beautifully fitting model, but no mediation whatsoever. There was pretty much no direct effect of these multiple representations on either errors or hints or time, and there was quite a substantial effect from these multiple representations directly to the post-test and directly to the delayed post-test. So this is a negative result, right? Either we don't have mediation or we left out some confounding. In experiment 2, we had the same problem. We had a beautiful model, right? And in fact, we had no mediation except for through errors, but the effect was negative. The overall effect was positive. So the direct effect was highly positive, but the effect through errors was negative, so the overall effect was slightly positive, if you believe this model. But in both cases, we got a negative result. We could not say that we had found the mechanisms by which, right, this was actually influencing learning. And we presented that to the field, and it was interesting because of that was the assumptions they were making for many years, and it turned out that we had some evidence, at least, that wasn't really what was happening. So it turned out, well, we might have been measuring these mediators incorrectly because there's sort of this non-monotonic relationship between the time you spend, the errors you make, right, and what you learn. So if this is the time spent, the students, right, who spend a really, really little amount of time don't learn much, and the students who spend a really, really, really lot of time don't learn much either. And it's different reasons, right? If you spend really little time, you're lazy, right? And if you spend a whole lot of time, you're just struggling, you don't get it. And so this is just right. So, and that's actually true for time spent. So we did a transformation of all three of these variables so there would be a monotonic relationship, monotonic variable. Didn't matter, actually it was worse. We tried lots of different things. So everything we tried didn't work. I won't go through this because I'm out of time. But the conclusions we said were, we know multiple representations seem to increase learning, but the standard variables, time, error, and hints, do not seem to be mechanisms through which they increase learning. It's possible they are, and we had latent confounders, but we had no evidence that they were. And so now, Martina is going to take over and show you what we did for the next series of experiments where we fared a lot better.
Don't need to. Yeah, so this is where I come in. Informed mediators. And before I get into those, I want to back up just for a second and give you some input on some learning sciences theory that informed the studies I've been conducting. So think of pretty much any domain you want. And learning in most of these domains that you're thinking of right now, which doesn't have to be fractions, will include some sense-making processes and fluency-building processes. So sense-making processes are learning processes that involve conceptual reasoning about why certain things happen. And fluency-building processes involve just gaining, being able to do things fast and effortlessly, pretty much. So, for example, if you think about how you learned about multiplication, coming to understand multiplication as repeated addition and making sense of multiplication that way is an example of a sense-making process. And just knowing multiplication facts would be an example of a fluency building process. So in terms of fractions, when I think about how students make connections between these different representations to understand that they all show the exact same abstract concept, which is a fraction, understanding or sense-making processes mean that students understand what the numerator corresponds to in each of these representations, and fluency building processes mean that they come to just by relying on perceptual properties of different representations, be able to solve comparison tasks fluently without thinking about numerator and denominator separately, for example. So, and I think there's a lot of agreement that both of these different learning processes play an important role. They even play an important role when you think about how you learn a musical instrument or a sport. But what we don't really know is how these different processes interact. And also what we don't know is whether they can compensate for one another. So that is a question that I wanted to investigate in the fractions tutor. Do we actually need to support both of these learning processes, or can we support one of these learning processes? Would that be enough? And in which order should we support these different processes? So how do we support sense-making processes? We gave students problems like these, where they had to go through very much step-by-step reasoning about how these different representations correspond to one another, and also doing some comparison tasks in this case. How do we support fluency building processes? We pretty much told students to just solve problems like this very fast, where it wasn't possible for them to rely on counting strategies, for example, but we wanted them to really just get experience in making use of perceptual properties in sorting equivalent fractions in this case. So in my experiment, I compared what happens if we give students sense-making support alone, fluency building support alone, or both together. What I found was just what I had expected, that the combined condition led to the best learning gains established by pre, post, and delayed post-test, just as Richard was showing earlier. And that, yeah?
So on average, combined condition was better on average?
On average.
Or on average through all the kids? I'm just thinking, what if one person learns better one way, another way?
Right, but there weren't any differences in terms of standard deviation between conditions or anything. If that's what you're getting at. Yes. Yeah, it's possible, but no, I did test for interactions of the condition effect with prior knowledge, for example. That's all I have data for, but it's entirely possible that there are more in-depth variations of some sort. But yeah, so I could have just leaned back and said, oh, okay, I'm happy with this result. But actually, it was really interesting because this was the best condition, which is fine, but then neither fluency building support alone or sense-making support alone led to better learning gains than none of these types of support. So that's surprising. It wasn't an additive effect, it was really an interaction. And that's where it really started to become interesting to me, because that's what I hadn't expected. Because that leads to a new question. It leads to the question, how do these two different learning processes interact? Since neither type of support alone is effective, but only taken together they enhance learning. So perhaps sense-making support enables students to benefit from fluency building support, or it could be the other way around, that fluency building support enables students to benefit from sense-making support. And that's a question that we didn't know the answer to at that point. So if I want to make the argument that sense-making support enables students to benefit from fluency building support, I might argue that students first need to know what the corresponding aspects between different representations are before they can build up fluency in making those connections. And that's what I'll call the understanding hypothesis. And the understanding hypothesis would actually make some predictions that we can test with a mediation model. It would predict that students who receive sense-making support in addition to fluency building support, compared to students who receive only fluency building support, that these students show better performance on the fluency building problems in the tutor because they have the kind of knowledge they need to actually benefit from those. And that should mediate the effect of condition on post-test and delayed post-test. So if I want to argue the other way around, I'll call that the fluency hypothesis. I might argue that if students gain some perceptual intuition about which representations correspond to one another, that will decrease cognitive load that they have to invest in actually making sense of those connections. So maybe it will be a little bit easier for them to engage in these sense-making processes. And that too I can test with a mediation model because that hypothesis makes the prediction that students who receive the combined version of sense and fluency building support versus fluency building support only, that these will show better performance on the sense-making problems because this perceptual fluency or perceptual intuition helps them learn from these problems. And that again should explain the effect of condition on my post and delayed post-test. So, but now the question is also, which mediators should I consider when I'm testing these models? Here's again both of them together. They actually are not mutually exclusive. It's entirely possible that both of them are true, both hypotheses. So as Richard was mentioning, our search among potential variables using just the general error rate, time spent, and hint use were not successful. What we did this time around was we used a knowledge component model that basically underlied the tutoring system and these problems for sense-making and fluency building support. So what did that look like? Here's an example of a screenshot I showed earlier. A knowledge component model is basically a way of annotating steps in the tutor that practice the same skill. So it's not too important that you can read all of this, but here's a step that a student needs to do where the student enters a numerator. And here again, the student enters a numerator. So presumably that practices the same skill. So we can pretty much just annotate our log data by these knowledge components. And then we still had a lot of those knowledge components, and I needed to find a way to size them down to include them in the mediation model. So what I did was I used two criteria. One was, is the number of, I looked at errors. So is the number of errors that students made on these knowledge components a significant predictor of their post-test performance? And second, are there significant differences between conditions on this variable? And so if we now consider, let's consider the understanding hypothesis first. These are the knowledge components that I selected for this model. So these are errors made on steps that corresponded to these three knowledge components. And this was a hypothesis model, which unfortunately didn't fit the data really well. For the fluency hypothesis, I again looked at knowledge components that matched my two criteria. These are the two that I selected. And unfortunately, the model didn't fit very well. But as we all know, there are very many alternative models that would be consistent with my two hypotheses. I do have some knowledge about the data, right? I know that the pretest is independent of condition assignment because I assign students individually and randomly to the condition. I know that the pretest is prior to whatever they did on the tutor, and I know that the pretest happened before the post-test, and so forth. But even with that, there are over 1 million possible alternatives just for the understanding hypothesis model. So here's what I found using the GES search in Tetrad for the understanding hypothesis. And here I marked all the paths that essentially show a positive effect of condition on the post-test and delayed post-test in green, and all the negative effects, negative mediations in red. So what's interesting is we have one negative effect here going through the name circle mixed error. That is a knowledge component that was possible only early in the tutoring system's curriculum. And also in some sense, it absolutely makes sense that we see a negative effect of some sort if we give students a larger variability in tutor problems that they work on. So just by virtue of having larger variability and less practice on these two different types of problems, we should see some negative effect of that. And if we add it all up together, the positive mediation is a lot stronger. So this model is in line with the understanding hypothesis that if I get sense-making and fluency-building support, I will perform better on knowledge components that play a role in the fluency-building problems. And that explains the positive effect of condition on the post-test. So now, here's the model that I found for the fluency-building hypothesis. And here, it's different. So we only see a negative mediation. And again, that is expected because students in the sense and fluency condition have more variability in terms of what problems they work on. So that's not surprising. And we have a direct positive effect, but no mediation of a negative effect. So here we see some evidence of a cost of having sense-making and fluency-building problems, but we don't see evidence that is in line with the fluency hypothesis. So looking back at the two hypotheses, we found some support for the understanding hypothesis. We did not find support for the fluency hypothesis. And just stepping back a second and taking stock of what we've learned, the results are in line with the understanding hypothesis, not with the fluency-building hypothesis. In terms of, well, meaning that students make more errors on the fluency-building problem, fewer errors on the fluency-building problems if they receive sense-making support in addition to fluency-building support. But there are certain limitations to this model, and the most important one, I think, is that in this experiment, students always received sense-making support before fluency-building support. So it's entirely possible that if I had presented fluency-building support before sense-making support, I would have gotten entirely different effects. But on the upside, I get a testable prediction, which is that if sense-making support enables students to learn from fluency-building support, which is the understanding hypothesis, then perhaps students will learn better if I present sense-making support before fluency-building support. So guess what I did in my next experiment? I compared two conditions, one that received sense-making support before fluency-building support, and then one that received fluency-building support before sense-making support. And it was really exciting to see that, in fact, the prediction that I got from the causal path analysis worked out. The sense-making before fluency-building condition had better learning gains at the post-test while controlling for pre-test than the fluency sense-making condition. And even more excitingly, I did another causal path analysis where I found that, in fact, I could replicate that same effect, that sense-making support enables students to benefit from fluency-building support by reducing the errors that students make on those problems. And the opposite was true for the fluency sense condition. So receiving fluency-building support before sense-making support actually increased the number of errors that students made on the sense-making problems. And since you're all so familiar with the tetrad models by now, I can just actually show you what these models look like. So this is the model for the fluency-building errors. For the understanding first, or the sense-making then fluency condition. And we see that by reducing the errors that students make on the fluency-building problems, I get a mediation of the effect on the post-test. This was a lab experiment. I didn't have a delayed post-test with these students. Here's the model for the sense-making errors. So, oh, I was really fast, actually. I'm sorry. More time for questions, which is good. But yeah, so students in the fluency first condition, they had an increase on errors that they made on the sense-making problems, which explained their worst performance compared to the sense-making first condition on the post-test. So in conclusion, I started out by asking, do we need to support both sense-making and fluency-building processes? That was my hypothesis. I found that yes, we do need to support both of these learning processes, but then surprisingly, I also found that neither type of support alone was effective, so that led me to do causal path analysis to find out how this interaction between these two different learning processes actually played out. And then that provided me with some additional hypotheses that I could then test in a follow-up experiment, and then use causal path analysis again to verify what the mechanisms were in that experiment. And it was nice that those data aligned in experiment 3 and 4. So I view this as an example in how we can really use causal path analysis to make sense of the data in more depth that we get, and also make a decision what kinds of interventions we want to investigate in the future. I think if I hadn't done the causal path analysis on this interaction effect, I might have done a completely different experiment, but also by understanding, or at least having a good hypothesis about what the mechanisms are, I get a much better sense of what other experiments I might be doing if I want to look at this, whether this is true in other domains than fractions now, which is what I'm working on now that I'm in Wisconsin. But yeah, and overall, what Richard was talking about was that these overall measures that have been typically used in ITS research of just overall problem-solving behaviors like errors and time spent and hint use, that these weren't successful for us in establishing the mediation between the different conditions that we compared. But then the informed mediators that we selected based on a knowledge component model, since they were much more fine-grained, they actually helped us understand these different learning processes much better. And then the model search helped us identify models that made sense given our hypotheses, and also then led to testable predictions, which we investigated further. So yeah, thank you very much. Yeah.
So I'm interested in whether your causal analysis is causal for the acceptance of your findings, conditional on the fact you did an experiment. It's clear that you derive value from doing the causal analysis. It's like your secret weapon, and it's great. Driving what experiments you do, and that's fantastic. I'm wondering how your colleagues react when told, not only did you do the experiment, but you also had the observational analysis, and whether the observational analysis, the causal discovery work, contributes to their interest in and acceptance of the findings.
Oh.
Yes.
How would I know?
Very quick.
Best paper
award. The work that she just presented was given a best paper award, the educational data mining.
Would have been given a still better best paper if she hadn't shown the graphical models.
No, I don't think so.
That's the question. Well, so you feel like it.
Well, we have no evidence for that.
Well,
Except anecdotal.
What did
Yeah.
you were saying?
I don't know what people say about me, really. Ask my colleagues. I think they like me. They recently gave me a job. So. Well, I hope so. I think it's always good if you can make an argument on what experiments you choose to do next by backing it up with data and causal models. I think. I would buy it. I would buy it if I wasn't me. I don't know who's next. Yeah.
I guess so.
Okay.
I'm interested in how the KC refined errors, the knowledge component, sort of refinement of the error measures, like what that's helping you with, and I'm wondering if maybe Are those, like, do you have any sense of maybe are those knowledge components on which it's more likely or less likely that students could make sort of shallow errors, or that they might be indicative of shallow versus deeper learning? Because I've been thinking about this a lot actually myself, and these measures we have that are very coarse-grained about errors or hints or whatever. It seems that there ought to be, well, in some ways in the cognitive tutor we know that certain errors correspond to more shallow, sort of just looking at a number in the problem and using it in the problem.
Yeah, well, it's always tempting to make up a story post hoc.
Yeah.
But I do have, when I looked at the errors that I ended up not selecting compared to the errors or knowledge components that I did select, it seemed to me that the knowledge components that I did select were much more conceptually challenging.
Okay.
Like placing a 1 on a number line given some dot that you're told shows 3/4 or something. That's a really difficult step. Other steps aren't so difficult, like finding a numerator, especially when the numerator is 1, is relatively easy. And those seem to be the ones that were more likely to be excluded from the analysis. But I'm actually, I think this highly selective nature of the analysis and the way I mean, of course we couldn't have included all knowledge components that were part, but it was highly selective, and I think that's a weakness of that analysis. But then in experiment 4, I actually, since it was a lab experiment, I was able to include all knowledge components just because there weren't that many, because the instructional time was a lot shorter, and I still found the same effect. So that's promising. But yeah, I'm not so happy with the highly selective nature of the experiment 3 analysis. But, yeah.
I have a little trouble linking up Richard's talk and your talk in terms of multiple representations. Was that just sort of stopped because at that point where you said that you couldn't really nail down what was going on about the effect of multiple representations? It struck me that there were a lot of psychological theories.
Yeah, the connection is in this graph and the next one, that the understanding first versus the post-test, right, are completely screened off by the error rate, equiv FL, and the pre-test.
Yeah, I mean, that's not, so you weren't able to find.
No, so
that was it?
What that shows is, right, that there is no direct effect from understanding first to post-test. So we can verify that. In the first experiment, anything you find the dependence, you can't verify that.
Well, so you have no explanation for the effect of multiple representations then?
Oh, you mean what is the mechanism by which multiple representations affects these knowledge components?
I think
there's a theory of multiple representations in psychology and why they're important, and they don't have to do with these observables that you have. And there are other ways of observing them, and I don't know that you've measured any of those.
So I think what you're asking is to tell us
data.
Well, I mean, the fact that we're getting the mediation here, I think is evidence that we found a mechanism. Right? Whether or not I can theoretically, or she can theoretically describe it in a way that you understand and recognize, I think is a good question. I'll let her answer.
Well, I think actually
what is the mechanism for yours is what you're saying?
No, I think what you're asking is we did compare different conditions in these different models. What Richard was talking about was the difference between single and multiple representations. And here in my condition note, I only have multiple representation conditions, so I'm not looking at the same question anymore.
Right.
But we do have. Yeah, so I think neither of us were really talking about multiple representations being effective in particular. But I think we were talking about using the latest experiment data that did also have a single representation control condition, which experiment 4 did not have, but experiment 3 did have. We just didn't include it in these, so we should still do that.
So we have not discovered, even with these later results, no way multiple representations.
No, we haven't looked at it yet.
That's a very big issue.
We haven't looked at it yet in that experiment 3 data set.
Yeah.
So I was just wondering, you're interested in how to increase learning, right? But you can only measure how to increase test scores. And is that the same, or is...
No.
So can you, what do people do about that? That's just,
Well,
test scores the best you can do, I can
Make better
understand.
tests. I mean, what else can professors be involved?
Yes,
well, it's always a trade-off because we want to motivate teachers to collaborate with us and use the tutor in schools. So we need to make a point that we can actually increase the test scores they care about, which are standardized test scores. So we do include those items in the test, but it's not the only test items that we have in the tests. So that's one way. We have more. I'm not a big fan of the standardized test items that are. I think there are several problems with them. I think some of the test items that we had on the tutor were better than that on these post-tests. But also we can look at error rates, for example, as students work on problems that include knowledge components of a certain kind. Do they become better? Do they become faster? Are they less likely to make errors as they progress through the tutor curriculum? We can look at things like that. And yeah, we can also look at future learning, which we haven't actually done, but I'd love to do. If we give them more instruction on a related topic, especially when you talk about fractions, there's always this argument that fractions are really foundational for later algebra learning. So I'd be very, very interested in using instruction on algebra and seeing if students are better learners in algebra after they do the tutor. But that's difficult to do. But hopefully somebody will do that in the future, if not myself. Yeah, but I think that's a really good point that you're making. Yeah.
Go ahead. Sorry. I've got the animal there.
Okay.
I'm wondering whether you looked at other outcome variables in your experiment before. So currently you're looking at the scores. And so what occurred to me is that you might also see the time students spend on the test or spend on learning is less when it's sense making and then fluency.
Yeah, we didn't see that, but we did have a bunch of other measures. We actually had interview data. So that perhaps also gets at your question. Using retrospective interviews, we found that students in one condition had much more conceptual reasoning about what fractions are than students in the other condition. We also had eye tracking data, and the results weren't quite as clear, but in part also because we don't really know what successful eye gaze behaviors are. So that analysis is still not really complete but I did do some correlations with test outcomes and also these error rates using that as a way to make sense of the eye tracking data. And it seemed like perhaps there was more connection making actually happening in one condition over another, but I'm a little bit hesitant to actually put out such a strong statement because I don't think the data was that clear.
But you didn't look at time.
I did look at time, but there was no difference. Yeah. Yeah?
So just from my general understanding, there are some children who have difficulty abstract thinking and conceptualization, but they're pretty good at learning, internalizing rules and applying them. For those students, I would imagine I could understand would be the opposite, I can't remember your fluency first. But once they get the fluency, then they get enough confidence that they can start. And might it be that there's just more students who are conceptual versus the other in this?
Yeah, I'm looking in my research that I'm just getting started with in Wisconsin. I'm going to look more at this interaction between sense making and fluency building, and I'm also going to look at some other measures such as self-efficacy and mental rotation ability. I'm going to do this in chemistry, not in fractions. But in this lab experiment, I don't think we just it was for a lab experiment. It was sizable. We had 78 students, I believe. But it's still, in these kind of sterile environments, it's more difficult to measure such things, I believe, than if you're in a school and the kids use the tutoring system as part of their regular math instruction. Then you might.
I think you're right.
Yeah.
One of the ways to explain this is to say there's just a higher proportion of children who tend to be sense-making first kind of students than there are.
Right.
But there should be, I'm assuming there are psychological tests which can reveal right away what sort of, whether the students are on one end of the spectrum or the other.
I don't know, are there?
If you know any?
Yeah.
Find me to.
I mean, there's all sorts of stuff on this.
I mean, you could use all kinds of techniques on the data you have to see if the subjects, the students, fell into interestingly different groups in their reaction.
Yeah, and there's actually
that doesn't require
a nice bit of work that some of our other students did in the machine learning class, where they did cluster the students into, I think, 5 groups, 4 groups, and they were trying to figure out which groups would actually get the learning. And it turns out some of the groups asked for help all the time, no matter whether they needed it or not. They didn't learn much. Some of the groups never asked for help, whether they needed it or not. They didn't learn much. Some of the groups asked for help, sometimes not others, and they learned. And no.
There was one group that didn't learn.
One group didn't learn, but there was a group that learned the most that were sort of being very stubborn about asking for help, and they learned the most from multiple representations. And that was a different.
That was the 2000. That was the experiment 2 data. So it'd be interesting to repeat that on this one. Though I'm not sure the lab experiment yields enough data.
But that's a good point. So I mean, I think there is this really interesting extra project, which is to cluster the students and to see who's actually.
Those would be the Carol Dweck type of kids, right? Yeah, basically.
Yeah, but it's. I mean, that's also why this field is really interesting, because we don't really know what the good variables are that we should be looking at. So I think.
Just about the fluency and the sense making. I mean, you know, there seems to be there are 2 different stories. One is the, standard proceduralization would say that you have to have declarative before procedural. I mean, but I think that the other side of that coin, and it depends on your knowledge components really, and how exactly they get implemented. We sort of saw it, but we didn't really, if the from the fluency side, you're actually sort of learning by rote some procedures, sort of like some sequences. Then that would be another route where actually that could come first.
Yeah, that's
so I
true.
think you have sort of asymmetrical processes going on.
I understand what you mean, though I would question that the fluency corresponds to procedural knowledge.
Well, that's really the question. Yeah. So
but I think that's an open question.
Right.
Yeah.
Okay, let's thank both of our speakers.